All right, this is CS50, and this is week 8. So for the past several weeks, we've been focusing on first Scratch and then C. And now today, do we introduce another language altogether, that of Python. Indeed, even though we've spent all this time talking about C and hopefully understanding from the ground floor up what's going on inside of a computer and how things work, the reality is that C is not the best language with which to solve a whole lot of problems. Indeed, as you yourselves might have realized by now, the fact that you have to manipulate sometimes memory at its lowest level, the fact that anytime you want to get something real done, like add capacity to a data structure or grow a string, you have to do all of that work yourself, means that C really creates a whole lot of work for the programmer. But ever since C's invention many years ago, has the world developed any number of new languages, higher level languages, if you will, that add on features, that fill in gaps, and generally solve problems more effectively. And so today we start to do exactly that transition, having motivated this just a week ago with our look at machine learning. Indeed, one of the tools that we used to have that conversation was to introduce snippets of this language, Python, because indeed it is much more of a well-suited tool than something like C. But let's begin this transition now. We, of course, started this conversation many weeks ago when we looked at Scratch. And yet, even though you probably found it pretty fun, pretty friendly, and pretty accessible, the reality was that built into Scratch was quite a lot of features, loops, and conditions, and customized functions, and variables, and any number of other features that we then saw the week after in C, albeit a little more arcanely with more cryptic syntax, but the expressiveness of Scratch remained within C. And indeed, even today, as we transition to another language altogether, you will find that the ideas remain consistent. And indeed, things just get easier in many ways to do. So we transitioned to C, and today we transitioned to Python. And so let's, just as we did with Scratch, try to convert one language to another, just to emphasize that fundamentally the ideas today aren't changing, simply the way of expressing it. So this perhaps was the very first program we looked at in C, arguably the simplest, and yet even then there was quite a bit of overhead. Well, starting today, if you wanted to write a program that does exactly that, voila, in Python, you simply say what you mean. If you want to print hello world, you literally in a Python program are going to write print, open parenthesis, quote unquote, hello world. And you can even omit the semicolon that might have hung you up so many times since. Now, in reality, you'll often see a slightly different paradigm when writing the simplest of programs. You might actually see some mention of main. But it turns out that a main function is not actually required in Python as it is in C. Rather, you can simply write code and just get going with it. And we'll do this hands-on in just a bit. But you'll find that a very common paradigm is to actually have code like this, where you do, in fact, define a function called main. And as we'll soon see through quite a few examples, this is how now in Python you define a function. You literally say def for define, main if that's the name of the function, open paren, close paren, and maybe 0 or more parameters therein. And then a colon and an absence of the curly braces with which you might now have gotten so familiar. But then indented beneath that, generally 4 spaces here, would be the code that you want to execute. And we'll come back to this before long, but this is just a common paradigm to ensure that at least one function in a Python program is called by default, and by convention we'll see it's called main. But the reality is that the program can now be as simple as this. So let's distill some of the fundamentals that we first saw in Scratch, then saw in C, and now see in Python as well. So Python has functions, and it also has something called methods, but more on that when we talk about object-oriented programming. But a function in C for printing hello world might have looked like this. Notice the printf for printing a formatted string. Notice the \n that's inside there. Notice the semicolon. In Python, it's indeed going to be a little simpler. We can distill that to just this. So we're not going to use printf. We're just going to use print. We don't, it turns out, have to have the \n in this example. You're going to get that for free. Just by calling printer, you're going to get a trailing new line printed, and we don't, again, need the semicolon at the end. Well, what about loops? Well, in Scratch, we had the repeat block, we had the forever block, and some other constructs still. In C, we had things like for loops and while loops and do while loops. Well, let's do a couple of conversions. In C, if you wanted to do something forever, like print hello world again and again and again, never stopping one per line, you might use a while loop like this. In Python, you're going to do something pretty similar in spirit, but it's going to be formatted a little differently. We still have access to the while keyword. The Boolean value true now has to be capitalized with a capital T. And again, instead of using curly braces, you're going to use a colon at the end of this statement and then indent all of the code beneath it that you want to happen cyclically. And again, we've borrowed print hello world from before, so no semicolon necessary there, no F, and no \n is required. Meanwhile, if we had a for loop in C that we wanted to say print hello world 50 times, we might use a fairly common paradigm like this. Well, in Python, you can do this in any number of ways, but perhaps one of the most common is to do something like this. To literally say for I in range 50, more on that in just a moment, and then print hello world. So this is shorthand notation, and this is perhaps the first instance where you really see just how pedantic, how much C belabors the point, whereas in Python, you just with higher frequency, just say what you mean. So for implies a looping construct here. I is declaring implicitly a variable that we're about to use. And then what do you want I to be? Well, you want it to be in a range of values from 0 up to, but excluding 50. So you want to go from 0 to 49 effectively. And the way you can express that here is as follows. You call this range function, which gives you essentially a sequence of numbers starting at 0, and then 1, and then 2, and then 3, all the way up to 49. And on each iteration of this loop, does I get assigned that value? So functionally, what we've just done is equivalent to what we've just done here, but it does it in a more Pythonic way, if you will. We don't have access to that same for construct as we did in C. We actually have something that's a little easier once you get used to it to use. Now, how about variables? Well, recall that in Scratch we had variables, those little orange blocks, and we didn't have to worry about the type. We could just put in numbers or other such things into them. Then in C, we had to start caring about this. But we had Booleans, and we had floats, and we had doubles, and chars, and strings, and long longs, and a few others still. Well, in Python, we're still going to have a number of data types, but Python is not nearly as strongly typed, so to speak. Whereas in C, and languages like C++ and a few others, you have to know and care about and tell the compiler what type of value some variable is. In Python, those types exist, but the language is more loosely typed, as we say, whereby they have types, but you, as the programmer, don't have to worry about specifying them. A bit more like our world from Scratch. So whereas in C, we might have declared an integer called I and assigned it an initial value of 0, we might have used syntax like this. In Python, it's going to be similar in spirit, but a little more succinct. Again, just say what you mean. I gets 0 with no semicolon, no mention of the type. But insofar as Python supports numbers, it's going to realize, oh, that 0 looks like an integer, is an integer. I'm going to define ultimately I as of being of type int. Meanwhile, we have Boolean expressions in Python as well, and these actually translate perfectly. If you have an expression in C testing whether I is less than 50, this is the same thing in Python as well. You literally use the same syntax. If instead you wanted to generally compare two variables, just like we did a few weeks back in C, you might do x less than y. Same exact code in C, in Python as well as in C. Now, how about conditions? So conditions are these branching constructs where we can either go this way or maybe this way or another way. So it's the proverbial fork in the road. Well, in C, if you wanted to have a loop, or rather an if statement that has 3 different branches, you might do something like this. And as you may recall, these curly braces are not strictly necessary, simply because we have one line of code nested beneath this if, and one line of code beneath this else if, and one line of code beneath this else. Technically, and you might have seen this in section or other resources, you can actually omit all of these curly braces, which, to be fair, makes the code look a little more compact. But the logic is pretty straightforward, and we saw similar yellowish blocks in Scratch. Now, in Python, the idea is going to be exactly the same, but some of the syntax is going to be a bit different. So if we want to say, is x less than y, we still say it, but we don't need the parentheses. In fact, if they don't add anything logically, we're just going to start omitting them altogether as unnecessary. We do have the colon, which is necessary at the end of the line. We do have consistent indentation. And those of you who have not necessarily had 5 for 5s out of for style, realize that in Python, the language by design is going to enforce the need for indentation. So in fact, I see myself being a little hypocritical here as I inconsistently indent this actual code. So this would not actually work properly because I've used a variable amount of spacing. So Python's not going to like that. And in fact, that's why I made that mistake, to make this point here so that you actually have to conform to using 4 spaces or some other, but being consistent ultimately. So notice this. This, not a typo. I didn't make that many mistakes here. Elif is actually the keyword that we use to express else if. So it's simply a new keyword that we have in Python, again, ending the same line with the colon. And then here, logically, is the third and final case. Else, if it's not less than and it's not greater than, must in fact be equal to. So we've used print as before to express these 3 possible outputs. Well, what about things like arrays? Well, Scratch had things called lists that we essentially equated with arrays, even though that was a bit of an oversimplification at the time. Python also has effectively what we've been using and taking for granted now in C, that of arrays. But it turns out Python, we're going to start calling them lists, and they're so much easier to use. In fact, all of this low-level memory management of having to allocate and reallocate and resize arrays potentially if you want to grow or shrink them, all of that goes out the window. And indeed, this is a feature you commonly get in a higher level language like Python, is a lot of this functionality built into the language as opposed to you, the programmer, having to implement those low-level details. So for instance, whereas in C, particularly in a main function, we've been using for some time argv, which is an argument vector or an array of arguments at the command line. You might access the first of those with argv0. We're actually going to have that same syntactic capability. We're going to access, in particular, argv a little differently via an object called sys. So sys.argv, as we'll see, is going to be the syntax. But those square brackets are going to remain. And the ideas of arrays, now called lists, are going to remain as well. So what's a little bit different in Python? We're about to see a whole bunch of examples, and indeed we'll port, so to speak, convert or translate some of our previous C examples into Python. But what's the mental model that you need to have for Python? Well, all this time, C we've described as being compiled. In order to write and use a program in C, you have to write the source code, and you have to save the file in something.c, and then you have to run something like clang something.c in order to output from source code your machine code. And then that machine code, the zeros and ones that the Intel, usually CPU inside, understands, can actually be run by double-clicking or doing /a.out or whatever the program's name actually is. So as you may have realized already, this gets fairly tedious over time. Like every time you make a darn change to your code, you have to recompile it with clang or with make more generally, and then run it. To make a change, compile, run it. Make a change, compile, run it. Wouldn't it be nice if we could reduce those numbers of steps somehow by just eliminating the compilation step? And indeed, a feature you get with a lot of higher level languages like Python and JavaScript and PHP and Ruby is that they can be interpreted, so to speak. You don't have to worry so much about compiling them yourself and then running resulting machine code. You can just run one command in order to actually run your program. And there's a lot more going on underneath the hood, as we'll see. But ultimately, if we had a program that looks like this, simply a function called main, as we saw earlier, and we'll see some more examples of this soon, that simply prints out hello world, it turns out that you can run this program in a couple of different ways. We can either, in the spirit of clang, whereby in C we ran clang hello.c, and then /a.out. In Python, if this program is stored in a file called hello.py, where .py is the common file extension for any programs written in Python, we can distill those 2 steps, as we'll soon see, into just one. You run a program called Python, which is called the Python interpreter. And what that does underneath the hood for you is it compiles your Python source code into something called bytecode, and then proceeds to interpret that bytecode top to bottom, left to right. So this is a lower level implementation detail that we're not going to have to worry about, because indeed one of the features of this kind of language is that you don't need to worry about that, and you don't need that middle step of having to compile your code. But for the curious, what's going to happen underneath the hood is this. If we have a function like main that's simply going to print hello world, and we do run it through that Python command, what happens underneath the hood is that it gets converted first into something called bytecode, which fairly esoterically looks a little something like this, which you can actually see yourself if you run Python with the appropriate command. And then what Python, the interpreter, does is it reads this kind of code top to bottom, left to right, that we, the programmers, don't have to worry about in order to actually make your program do work. So you'll often hear that Python is an interpreted language, and that kind of is indeed the case, but there can indeed be this compilation step, and it actually depends on the implementation of Python that you're using or even the computer that you're using. And indeed, what we're now starting to see is a dichotomy between what it means to be a language and what it means to be a program like this thing Python. Python is a language. C is a language. Clang is a compiler. Python is also not just a language, but a program that understands that language, otherwise known as an interpreter. And so anytime you see me starting to run the command Python, as you will too for future problem sets, will you be interpreting the language, the source code that you've written? All right, so let's go ahead now and make a transition in code from the world of C to the world of Python. And to help get us there, let's put back on, just temporarily, some training wheels of sorts, a re-implementation of the CS50 library from C to Python, which we've done for you. And we won't look at the lower level implementation details of how that works. But let me propose that at least for part of today's story, we are going to have access to at least a few functions. These functions are going to be called getChar, getFloat, getInt, and getString, just like those with which you're already familiar. The syntax with which we access them is going to be a little different in this case. By convention, we're going to say CS50.getChar, CS50.getFloat, and so forth to make clear that these aren't globally available functions that might have even come with the language, because they're not. Rather, these are inside of a module, so to speak, that CS50 wrote that implements exactly that functionality. We'll soon see that Python has at least these data types: bools, true or false, whereby the T and in turn the F have to be capitalized in Python, unlike in C. Floats, which are going to give us real numbers, floating point values with decimal points. Int, which is going to give us an integer. And str, or string, which is going to give us the string that we've now come to know and love. But nicely enough, you can start to think again of string as an abstraction, because it's actually what's called a class that has a whole lot of functionality built in. No longer are we going to have to worry about managing the memory for our strings underneath the hood. Now, Python, realize, also comes with a bunch of other features, some of which we'll see today too. You can actually represent complex or imaginary numbers in Python natively in the language itself. You have the notion of lists, as we mentioned before, an analog to C's arrays. We have things called tuples. So if you've ever seen like x, y coordinates or any kind of groups of values in the real world, we can implement those too in Python. Ranges, which we saw briefly, whereby you can define a range that starts at some value and ends at some value, which is often helpful when counting from, say, 0 to 50. A set, which, like in mathematics, allows you to have a collection of objects. Then you're not going to have duplicates, but you're going to be it's going to be very easy to check whether or not something is in that set. And then a dict, or a dictionary, which is actually going to be really just a hash table. But more on that in just a bit. And these are just some of them that we'll soon see. So let's now rewind in time and take a look back at week 1 and perhaps this first and simplest example that we ever did, which is this one here called hello.c. And meanwhile, let me go ahead here on the right-hand side and create a new file that I'm going to go ahead and call hello.py. And in here, I'm going to go ahead and write the equivalent Python program to the C program on the left. Print hello world. Done. That is the first of our Python programs. Now, how do I run it? There's no clang step. And it's not correct to do just /hello.py, because inside of this file is just text. It's just my source code. I need to interpret that code somehow, and that's where that program Python comes in. I'm going to simply do Python space hello.py, and I don't need the / in this case because hello.py is assumed to be in the current directory. Hit enter, and voila, there's my first Python program. So what I haven't put in here is any mention of main. And just to be clear, we could. Again, a common convention in Python, especially as programs get a little more complicated, is to actually do something like this: to define a function called main that takes, in this case, no arguments, and then below it to have this line pretty much copied and pasted. If name equals underscore underscore main underscore colon, then call main. So what's actually going on here? Long story short, this line 4 and line 5 is just a quick way of checking, is this file's default is this file's default name, quote unquote, main with the underscores there? If so, go ahead and just call this function. Now, generally, we won't bother writing our programs like this when it is not, in fact, necessary. But realize all these 2 lines of code do is it ensures that if you do have a function called main in your program, it's just going to call it by default. That does not happen automatically. And indeed, if I just wrote hello.py like this and gave it a main function, gave it a code like print hello world, but did not tell Python to actually call main, I could run the program like this, but nothing's actually going to happen. So keep that in mind as a potential gotcha as you start to write these things yourself. Well, now let's take a look back at another program we had in week 1. This one might have had me doing this in string.c. So in string.c, did we introduce the CS50 library in C, and we also introduced from it the getString function. And to use it, we had to declare a variable like s of type string, and then assign it the return value of getString. Well, let's go ahead and do this same program in Python, this time calling it string.py. And I'm going to go ahead now and include the CS50 library. But the syntax for this is a little different in Python. Instead of pound including, you do import CS50. And that's it. No angled brackets, no quotes, no .h or anything like that. We have pre-installed in CS50 IDE the CS50 library for Python. And that's going to allow me now to do this. S gets cs50.get_string print hello world. And we'll fill in this blank in just a moment. But let's first see what's going on. On line 3 here, I'm declaring a variable called s on the left. I'm not explicitly mentioning its type because Python will figure out that it is in fact a string because the function on the right-hand side of this equal sign, cs50.getString, is going to return to s a value of type string. Now, as an aside, in C, we kept calling these things functions. And indeed, they still are. But technically, if you have a function like getString in this case that's inside of an object, that's inside of what's called a module in Python, like the CS50 module here, now we can start calling getString as a method, which just means it's a function associated with some kind of container. In this case, this thing called CS50. Now, unfortunately, this program, of course, is not yet correct. If I do Python space string.py and then type in my name, David, it still just says hello world. So I need a way of substituting in my name here. And it turns out there's a couple of different ways to do this in Python, some of which are more outdated than others. So long story short, there are at least 2 major versions of this language called Python now. There's Python 2 and there's Python 3. Now, it turns out, and we didn't really talk about this in the world of C, there's actually different versions of C. We in CS50 have generally been using version C11, which was the 2011 version of C, which just means it's the most recent version that we happen to be using. For the most part, that hadn't mattered in C, but in Python, it actually does. It turns out that the inventor of Python and the community around Python decided over the past several years to change the language in enough ways that they are breaking changes. They're not backwards compatible, which means if you wrote code in version 2 of Python, it might not work in version 3. And unfortunately, both versions of the language have been coexisting for some time, such that there's a huge community that still uses Python 2. There's a growing community that uses Python 3, so that we stay at least as current as possible. We, for the class's purposes, will use Python 3. And for the most part, if you're learning Python for the first time, it's not going to matter. But realize, unfortunately, that when you look up resources on the internet or Google things, you'll very often find older examples that might not necessarily work as intended. So just compare them against what we've done here in class and in section. All right, so with that said, let's go ahead and substitute in my name, which I'm going to do fairly oddly with 2 curly braces here. And then I'm going to do this, dot format, open paren, s, close paren. So what's going on here? Well, it turns out that in Python, quote unquote something is indeed a string, or technically an object of type str. And it turns out that in Python and in a lot of higher level languages, objects, as I keep calling them, have built-in functionality. So a string is no longer just a sequence of characters. It's no longer just the address of a byte of memory terminated eventually with \0. There's actually a lot more going on underneath the hood that we don't really have to care about, because indeed this is a good thing. We can truly now think of a string in Python as being an abstraction for a sequence of characters, but baked into it, if you will, is a whole bunch of additional functionality. For instance, there is a function that is a method called format that comes with strings now. And it's a little weird to call them in this way, but notice the similarity. Just like the CS50 library, or module, or really object, has inside of it a getString method or function, so does a string like quote unquote whatever have built inside of it a method or function called format. And as you might have guessed, its purpose in life is just to format the thing to the left. So you'll get used to this format, and there's no pun intended. And there's other ways to do this still, but we'll see why this is useful in just a moment. For now, it just looks like a ridiculously, unnecessarily complex way of plugging in a name to simply do this. If I type in my name, David, and hit enter, now I get hello, David. But trust for now that this is going to be useful as we start to use other file formats still. Now, as an aside, so that we've not just removed training wheels and now putting them back on you just for the sake of Python, let me emphasize that we can actually implement this program exactly the same way without using anything CS50 specific, using built-in functionality like the input function in Python version 3. The input function here optionally takes a prompt inside of its parentheses. But if I exclude that, it's just going to ask for some text. And here I can do this now. If I run python string.py and type in my name, it still works. And if I actually do something like this, name colon space, save the file and rerun it, now I get a prompt for free. So here too, super simple example. But whereas in C, typically we would have had to add that prompt. We're using printf and the loop again and again as needed. Here we can simply prompt once via the input function and get back a value all at the same time, such as, say, Zamila's name here. So we're only using the CS50 library for today's purposes to show you the equivalence of some of our C examples vis-a-vis these Python examples, but it is by no means necessary. It just gives us a bit more functionality that's useful. For instance, if I were to write a program very similar to this one, recall way back when we had this program in C, which simply got an int from the user and printed it out. Let me this time create a new file called int.py, and inside of it, import the CS50 library, which also has a function called cs50.getInt, and then use this function to simply say print, quote, unquote, hello, open curly brace, close curly brace, dot format, I, save this file, run python int.py. I can type in a number like 42. And voila, now we've used getInt. But now let's actually format something. You'll recall that in the world of C, we had some issues of imprecision. So recall that this program, whereby I printed the value of 1/10 to 55 decimal places, actually did not yield 0.100000 to infinity, as I was taught in grade school. Rather, we saw some raring of the head of imprecision, whereby floating point values in C were not represented infinitely precisely. And in fact, let's do this too. Imprecision.py shall be the name of this file. And you know what? I don't even need to write much code here. I'm just going to go ahead and print out somehow or other a value like, say, 1 divided by 10. Let me go ahead and save that, run python of imprecision.py. And I do get 0.1. So this is kind of interesting. And in fact, it's revealing a feature of Python. But I don't want to see just one decimal point. I want to do the equivalent of %.55f as we saw in Python. And it's almost the same as we saw in C. It's almost the same in Python. But instead of using that % sign, I'm going to use a colon instead. And now notice, inside of all of this is just 0.55f preceded by that colon. So it's almost exactly what we did earlier, but with a bit more specificity. And now I see again that ridiculously disappointing imprecision eventually, which we also saw in C. So it turns out in Python too, only a finite number of bits are used typically to represent a floating point value. So we still have, unfortunately, that issue of imprecision. But what we don't seem to have is something that we stumbled over some weeks ago. And in fact, the reason in the C version I did 1.0 divided by 10.0 was what? Why didn't I just do 1 divided by 10 in the C version? What happened? So as I recall, if you take an int in C and then divide it by an int in C, you get back an int in C. Unfortunately, 1 divided by 10 should be 0.1, but that's not an int. That's a floating point value. So we saw this issue of truncation with integers, whereby if you have a value 1 divided by a value 10, and both of which are ints, you're going to get back an int, the closest int after throwing away everything after the decimal point, which unfortunately would have been 0 if I didn't define them instead as being floats. But it seems that Python has actually fixed this. In fact, one of the features of Python 3 is to redress exactly this. For many years, we've all sort of had to deal with the fact that an integer divided by an integer is, in fact, an integer and therefore mathematically incorrect potentially. Well, it turns out that's been fixed such that now 1 divided by 10 gives you the value that you actually expect, not, in fact, 0. But what does this actually mean? Let me go ahead and open up an example that I wrote in advance, this one being a port, a translation of what we did in C some time ago like this. You'll recall that in the version we wrote weeks back, we just tested out the plus operator in C, the subtraction operator, multiplication, division, and modulo for a remainder. Well, it turns out we can do something almost identically in Python here if we look at int.py. But notice that just as I've changed the program slightly to use the CS50 library for Python to get a value x here, to get a value y here, notice that there's one additional example down here. I'm still demonstrating plus. I'm still demonstrating minus, multiplication, division, and what is this? So it turns out that in Python 3, if you want the old behavior and you actually want to do integer division such that you not only divide but effectively floor the value to the nearest int below it, you can actually use this syntax, which somewhat confusingly perhaps looks like a comment in C. It is not a comment in Python. In fact, in Python, as you may have gleaned already, comments typically will start with just a single hash symbol. But there's other ways to do comments as well. But notice one other curiosity too. This program does not print out new lines when prompting the user. In fact, if I run this program, let me go ahead and run this example, which again is called ints.py. Notice that it prompts me for an int x and an int y, and I supply the new lines. They don't get printed for me. And then we get back the answers that we hopefully expect here. But what is this going on here? Well, in the previous examples, I got away with not using \n anymore. On the one hand, that's nice. I don't have to remember this annoying thing that often you might omit accidentally, and therefore your prompt ends up on the same line, and just things look incorrect. Unfortunately, the price we pay by no longer having to pull at \n in order to get a new line from Python's print function is, if you don't want that freebie, if you don't want that \n, unfortunately, you're going to have to pass a second argument to the print function in Python that overrides what the default line ending is. So whereas you would be getting by default \n for free, if I instead say comma end equals quote unquote nothing, that means, hey, Python, don't use the default \n. Instead, output nothing whatsoever. So it's a trade-off. And again, much like you might have gleaned from the recent test, is there this theme of trade-off. So even in terms of the usability of a language, might there be this trade-off? If you want one feature, you might have to give up some other altogether. So let's just kind of tie this all together and implement a program together for temperature as follows. Let me go ahead and create a file called temperature.py. And this simply I want to use to convert, say, Fahrenheit to Celsius, to convert two temperatures. I'm going to go ahead for convenience and use the CS50 library. I'm going to declare a variable called f that's going to become, as we'll see, of type float by using CS50.getFlow or float. And now I'm going to declare another variable, c, for Celsius, that's going to equal 5 divided by 9 times f minus 32, which I'm pretty sure is the formula for converting Fahrenheit to Celsius. And then I'm going to go ahead and print this, not with printf, but with print, as follows. I'm going to have some placeholder there formatting this variable c. And what do I actually want to put inside of here? Well, if I want to go ahead and format it to just one decimal place, I'll use .1f. Let's go ahead and run Python on temperature.py, enter. Let's type in a temperature like 212, 100 in Celsius. Let's type in the only other temperature I really know, 32, 0 in Celsius. So we've done the conversion, and we've not had to worry nearly as much as we did a few weeks ago about all of the issues of integers being truncated when you divide. All right. So let's not focus so much on math and operators. Let's actually do a little bit of logic by way of this example from a while back. We had an example in C called logical.py, which simply did this. It asked me for a char, and it stored it inside of, and actually, this could have been this, char c gets get char. And then I compared that char c against y in capital letter or y lowercase. And if they matched, I printed yes. Otherwise, if it was capital N or lowercase n, I printed no. Else, I just said error. So it's just an arbitrary program that's meant to assess, did I type yes or no effectively by its first letter, capitalized or otherwise. Let's go ahead and port this, translate this to Python as follows. Let me go ahead and create a new file over here. We'll call this logical.py. And I'm going to go ahead as before and import the CS50 library. But again, you could just use Python's built-in input function to do this. But at least this way, I'm guaranteed to get exactly the data type I want. C gets CS50.get char. And then over here, I'm going to now say a condition. So remember some of the syntax from before. You might be inclined to start saying if open paren. But we don't need that here. We can instead just say if C equals yes, or C equals y, then go ahead and print yes. Now, this just seems ridiculous. Like, all these weeks later, finally, you can truly just say what you mean. And indeed, in Python, there's not going to be the same double vertical bar or double ampersand that we've used now for some time to express or and. Rather, we can really type this a bit more like an English sentence. It's still somewhat cryptic, to be sure, but at least there's less clutter. There's no required parentheses anymore. We don't need the curly braces even. We don't need vertical bars or ampersands. We can just use the word with which we're more familiar in the real world. But notice, too, I've done something subtly different from C. In the C version, to compare this variable C against y in capital letters or lowercase, I used single quotes. And why was that? Right? In C, you actually have a data type called char, and it's fundamentally distinct from a string. So if I'm checking a char in C against some hard-coded value, I have to use single quotes to make clear that this is just a single ASCII byte, capital Y or lowercase y. It's not capital Y \0. It's not lowercase y \0. It's just a single byte that I'm trying to compare. But it turns out in Python, there really is no such thing as a single char. If you want a character like capital Y or lowercase y, that's fine. But you're going to get an entire string, a string with just one character in it, plus whatever else is hidden inside of a Python string object. But what that means for us is that we don't have to worry as much about, is this a char, is this a string? Just compare it in the more intuitive way. In fact, notice, moreover, what I am not using. In C, when we started to compare strings, we used things like strcomp or string compare. No more. If you want to test two strings for equality, does C from the user actually equal y, capitalized or lowercase? We can just double quote it like this. And in fact, it turns out that it doesn't matter in this context whether I use double quotes or single quotes. Generally in Python, you can actually use either. I'll simply adopt the habit here and throughout these examples of using double quotes, if only because they're identical to what we've done in CS50 for C. But realize that both of these are correct. Stylistically, generally just be consistent with respect to yourself. All right, so let's do another example and start to build on this sophistication, because this isn't all that impressive that the, oh, and actually, this, of course, is not yet done. If C equals n, or C equals lowercase n, then I'm going to go ahead and print out, whoops, not with printf, but with no, else colon, I'm going to print out error. Almost forgot to finish my thought. So that's why the program is so short. Now it's almost as long, although again, if you ignore the curly braces, it's pretty much the same length, just a little syntactically simpler. All right, so let's build up something a little more interesting in the interest of design. So some weeks ago, we introduced this example in C, the purpose of which in positive.c was to implement a program that doesn't just get an int from the user, it gets a positive integer. And this was a useful opportunity way back when to implement a custom function of our own, a feature that we had in Scratch. But it also was a nice way of abstracting away what it means to be get positive int, because we could use get int underneath the hood, but not necessarily care about it thereafter. So in C, recall a few details. We needed, one, not only our header files up top, but we also need this forward declaration. We need this prototype at the top of the file, because C is going to read things top to bottom, left to right. So we better tell Clang, or whatever compiler we're using, about the function before we use it in the code itself. I now have an int I getting a positive int, and then I just go ahead and print this out. So the real magic seems to be below the break here, whereby we implemented getPositiveInt. And to do this in C, notice a few features. One, we declared it as a function, getPositiveInt, that takes no arguments and returns an integer. Inside of that, we declared a variable n outside the scope of the do while loop because we wanted n to exist both here and here, as well as when we actually finally return it. And then in this do while loop, we just kept pestering the user so long as he or she gave us a value that's less than 1, so non-positive. And then we returned it and printed it. Let's try to now port this to Python. In Python, let me go ahead now and do the following. I'm going to create a new file called positive.py. I'm going to go ahead and import the CS50 library as before. And I'm going to go ahead and define a main function that takes no arguments. We're not going to worry about command line arguments. And indeed, even when we are going to worry about them, we're not going to declare them inside those parentheses anymore. Now I'm going to go ahead and do getPositiveInt. And now I'm going to go ahead and print out with print. So placeholder is a positive integer, close quote. And then I'm going to do format I, plugging in that value. All right, so let me shrink the screen here a little bit so that things fit a little better on the Python side. And now that's it for main. No curly braces. I just unindent in order to now start my next thought, which is going to be this. I'm going to go ahead and define another function called getPositiveInt. I don't use void in Python. I simply leave the parentheses empty and add a colon at the end to say, here comes the function's implementation. And it turns out in Python, there isn't this do while construct. So the closest match to do while we did see earlier is just while. And a very common paradigm in Python is to deliberately induce, as you might have in C, an infinite loop. Capitalizing true, because in Python, a bool of type that's true or false is going to be capitalized. And then inside of this loop, let's go ahead and do the following. Let's go ahead and say print n is. And now below this, I'm going to say n gets int. But this is inside the CS50 module, so I need to do that there. And then I'm already in an infinite loop. So you know what? If n is greater than or equal to 1, I'm going to go ahead and break. So the logic is a little bit different this time. But I'm breaking out of the loop once I have what I intend. So I need to do one last thing. Once I've broken out of this loop, what do I need to do to complete the implementation of getPositiveInt? I've gotten it, but I need to hand it back to the user. So let me go ahead on this last line and return that value as n. So notice a few distinctions here versus C. Whereas in C, a few weeks ago, we had to give some hard thought to the issue of scope. Turns out we don't have to worry about that as much. As soon as I declare n here, it's going to be within scope within this function such that I can return it down here, even though that return statement is not indented and not inside, so to speak, that actual looping construct. Notice, too, because we don't have a do while construct, I had to re-implement it using while alone. And I actually could have done that in C. Do while does not give us any fundamental capabilities that we couldn't implement for ourselves if we just implemented it logically a little more like this. We're still printing out n is first. We're then getting an int. We're then checking if it's positive. And if so, we're breaking out and returning. There is one or two bugs in here. And we'll trip over these in just a moment. Let me go ahead now and save this file and then run Python positive.py, enter. Nothing seemed to happen. It's not running anymore. I'm back at my $ prompt. Let me try running it again. Python positive.py. I mean, there's no error message. And in the world of C, no error message usually meant something's right. And it's right. I've just kind of forgotten a key detail. I've imported the CS50 library. I've defined main. I've defined getPositiveInt, but what is different in this world now of Python? Main is not called by default. So if I want to actually call main, I better adopt a convention of, for instance, this paradigm. So if name equals main, then with a colon, actually call the main function. And technically, as an aside, this would still work even without this. We could simply put main down here. But let me wave my hand at that detail for now and just emphasize that anytime you want to proactively call main, if you've set up your code in this way, we should indeed do it like this. Let me go ahead now and rerun Python positive.py. N is 42. N is a positive integer. Let me go ahead and run n is and then 0. Nope. -1. Nope. Foo. Retry. That's the CS50 library kicking in, noticing that's a string. Let's try 50. And OK, that worked. Now, the bug I alluded to earlier is just that this looks stupid. Having the cursor now on the next line, I can fix this, recall, by adding the second argument, whereby the line ending for print is just quote unquote. Let me go ahead and rerun it. N is 42. And now things look a little bit cleaner. Now, at the risk of complicating, let me just point out one other detail. Technically, I could also do this. If you don't need a main method or main function, then why do I have it at all? It stands to reason that I could just write my program like this. Yes, I'm defining an additional function, getPositiveInt, and that's going to work as expected. But technically, if I don't need a main method, and all of the simple examples we've done thus far just have me writing code right in the file itself and then interpreting it at the command line, I should be able to do this, I would think. So let me try this. Let me go ahead and run, again, Python positive.py, but on this new version, enter. And now we get the first scary looking error message. So traceback, most recent call last, file positive.py, line 3, and module I getPositiveInt. Name error, name getPositiveInt is not defined. So the first of our Clang-like error messages, this one coming, of course, not from Clang, but from the Python interpreter. And even if the first few lines are indeed pretty cryptic, name error, name getPositiveInt is not defined. But yes, it is. It's right there at the moment on line 6. So it turns out Python's not all that much smarter than Clang when it comes to reading your code. It, too, is going to read it top to bottom, left to right. And insofar as I'm trying to call getPositiveInt on line 3, but I'm not defining it until line 6, unacceptable. Now, you might be inclined to fix this like we did in C, whereby you say, all right, well, let me just do getPositiveInt up here, maybe, and just put a prototype. But this now looks especially weird that this now looks like a function call, not a prototype, because we're omitting now the return type because there is none. And there's no semicolon here by convention. And indeed, if I do this again, it's the same error. Now the problem is I'm calling it in the wrong place even earlier on this line, still line 3, in addition to line 5, which is now there. So how do we fix this? Well, back in C, we didn't technically need prototypes in most cases. We could instead just kind of work around it by moving the code to, say, the top of the file and ignore the problem, really, and now run the program, and now it's back to working. Why is that? Well, the Python interpreter is reading this file top to bottom, left to right. It imports the CS50 library. It defines a new function called getPositiveInt. And then on lines 11 and 12 now, it uses that function and actually then prints out the return value. But again, this very quickly gets a little messy. Now to find what this program does, I have to kind of look all the way at the bottom of the file just to see my code. It'd be nice if like the actual logic of the program were at the top of the file, as has been our norm with C, putting main up top. So another good reason for having a main method is just to avoid these kinds of issues. If I rewind all of these changes that we just made and go back to this last version, this avoids all of these issues, because if you're not calling main until literally the last line in your file, it's going to be defined at that point. So is any functions that it defines. And all of that will be implemented for you. And so now we're good to go. So again, we're complicating the program deliberately, but to proactively address those kinds of issues. All right, let's introduce one other topic now. Abstraction has been a theme, not only recently in the test, but also in the earliest weeks of the course. Well, you might recall from those early weeks, we had examples like this, where we had an example called cough0.c, whose purpose in life was to do so 3 coughs in a row. Now, this was clearly copy-paste, because all 3 of these lines are equivalent, but that's fine for now. Let me go ahead and verbatim convert this to Python as closely as I can in cough0.py. Turns out it's pretty easy. Print, quote unquote, cough. And then I can really demonstrate how poorly designed this is by literally copying and pasting those 3 lines. I don't need standard.io.h. I don't need the CS50 library. I don't need main. We know, because now if I just do Python, cough0.py, enter, cough, cough, cough. All right, but we improved upon this example in C. Recall that in C, we then looked at cough1, which at least used a loop. So how do I do this in Python? Let me go ahead and save this now as cough1.py. And let me try to borrow some of the logic from earlier. Let me do for I in, and you know what? I'm going to do range 3. We had 50 before, but I don't need it to iterate that many times. Now let me just go ahead and print cough 3 times, and now run Python, cough1.py, enter, cough, cough, cough. All right, but recall in the world of C, we improved further in cough2.c as follows. We abstracted away, so to speak, what it means to be a coughing by wrapping it in its own function called cough, because we don't really care that cough is implemented with printf. We just like the idea, the semantics, if you will, of having a new custom function called cough. So let's go ahead and try to do that in Python. Let me go over here and create a new file called cough2.py. And in here, let me go ahead and define main as before. Inside of this, let me do for I in range 3. And let me go ahead here and call proactively cough, even though it doesn't yet exist. Let me go down here now and implement cough in such a way that it simply prints cough. Let me go ahead now and do Python cough2.py. Wait, something's wrong. What's going to happen? Nothing. I need to actually call the function. And again, the paradigm that we'll adopt is this. If the name of the file is the default name of quote unquote underscore underscore main underscore underscore, then let me go ahead and call main. So now if I run this again, voila, cough, cough, cough. Notice, again, no prototype, no import from CS50 because we don't need it. But let's improve upon this further. In C, we took this one step further and then parameterized cough so that we could cough 3 times, but not have to implement the loop ourselves in main. We just want to punt, so to speak, or defer to the actual implementation of cough to cough as many times as we want. So if I want to do that here, let me go ahead and save a file called cough3.py. And let me go ahead and, again, define main to just do a cough, but this time 3 times, actually giving it an argument. And then let me go ahead and define cough. Again, but not with open paren, close paren, but with an actual variable called n. Here, too, I don't need its data type. Python will figure that out for me. And then in here, I can do for I in range of not 3 anymore, but n, because that's a local argument that's been passed in. And now let me go ahead and print cough that many times. Down here, let me go ahead and do my if the name of this file is the default name of underscore underscore main, then go ahead and call main. So now let me run this, cough3.py, and I get cough, cough, cough. And you recall, we kind of took this to an extreme a few weeks ago. Suppose I now want to implement the notion of sneezing. Well, sneezing was deliberately introduced, not so much because it's all that useful per se as a function, but because it allowed me to factor out some common code. It would be a little lazy of me if to implement sneeze, I went ahead and did something like this, whereby I literally copy and paste the code, call this sneeze, and then say achoo here instead, because look how similar these two functions are. I mean, they're literally identical except for the words being used therein. The lines of code logically are the same. So instead of that, let me go ahead and port this as I did in C as follows. Let me go ahead and save this as cough4.py. And in here, go ahead and define main. And main now is going to call cough 3 times. And it's going to call sneeze 3 times, which just means I need to implement them. So let me go ahead and define cough as before, taking in an integer n, we can call it. But we could call it anything we want. But now, you know what? Let me generalize this and just have it call a say function with the word we want it to say and how many times. Meanwhile, let me go ahead and define sneeze as taking a similar int that simply says achoo, comma n, that many times. And now I just have to define say. And before in C, on the left-hand side here, took 2 arguments. We can do that as well in Python. We can simply say word and n without worrying about their data type and declaring them. And now in here, I need to do this for I in range of n. Let me go ahead and print word. Now, technically, if I really wanted to be consistent, I could do print quote unquote curly braces, format word, but I literally gain nothing in this case from doing that. So it's a lot cleaner and a lot more readable just to literally print the word. You don't strictly need that placeholder. Then down here, let's do if the name of the file equals main as before, call main, voila. Let's go ahead now and do Python of cough4.py, enter, cough, 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 achoo, achoo, achoo. So it's kind of an exercise in futility in the end, because like the program still doesn't do it with that anything that's all that fundamentally interesting. But notice how quickly we've moved from just printing something like hello world just a little bit ago to defining our own main function that calls two functions that are parameterized, each of which in turn calls some other function that takes multiple parameters. So we're already very quickly building up these building blocks even faster than we might have done in the earliest weeks of the class. All right, so that's essentially week 1 that we've now converted to Python. Recall now in week 2 of CS50, we started to look at strings. We looked at command line arguments. So let's now, with relatively fewer examples, compare and contrast what we did then to what we'll do now and see what new features we have. Recall indeed that in week 2, we implemented strlen ourselves. Before we even started taking it for granted that there is a strlen function that returns the length of a string, recall that we implemented it as follows. We got a string from the user. We initialized some counting variable like n to 0. And then while that location in the string using our square bracket notation was not equal to this special sentinel value, \0, do n++, thereby incrementing n, and then eventually print out what the value of n is. So this, though, assumed in week 2 an understanding of what's going on underneath the hood. In Python, we're not going to want to worry about what's going on underneath the hood. Indeed, this whole principle of abstraction, and more specifically encapsulation, whereby these implementation details are deliberately hidden from us, is now something we can embrace as a feature. No longer do we need to worry as much about how things are implemented, but just that they are implemented. So increasingly, will we start to rely on publicly available documentation and on examples online that use features of code, as opposed to worrying as much about how they're implemented underneath the hood. So toward that end, let me go ahead and implement the equivalent of this program in Python in a manner that would be appropriate here with strlen.py. I'm going to go ahead and import the CS50 library so that I can get a string like this with getString. And then I'm going to print the length of s. So recall, of course, in C, we could have done this with strlen. In the world of Python, we're not going to use strlen, but rather len, or len for length, which it turns out can be used on any numbers of different variables and objects. It can be used on strings. It can be used on lists and other data structures still. So for now, know that this is how we might print the length of a string. So let's go ahead and try this. Python of strlen.py, type in something like foo, which is 3 letters, and indeed, that's what we get back. Well, now let's actually take a look at the fact that we do still nonetheless have this notion of ASCII underneath the hood going on, although not necessarily ASCII, but Unicode, which is a far more powerful encoding of symbols so that we can have far more characters than just, say, 128 or even 256. Let me go ahead and create the following example. We'll call this ASCII0.py, so that it lines up to the example we did called ASCII0.c a few weeks back. And let me go ahead and do the following. For I in the range of 65 to 65 plus 26. So if I want to start iterating at 65 and then iterate ultimately over 26 characters like we did a few weeks ago, I can actually do this. I can say something like something is something, specifically if I format 2 values. I essentially want to format I and I again. But the first of these I want to actually print as a character. So it turns out that if you have in a variable like I, a decimal value, an integer, that corresponds underneath the hood to an ASCII value, or really Unicode value, which is a superset, you can call the chr function, which is going to convert it to its character equivalent. If I go ahead now and run Python of ASCII0.py, I've made a mistake. And you'll notice even CS50 IDE noticed this, and I didn't notice CS50 IDE. If I hover over that little x, it's yelling at me invalid syntax, because CS50 IDE actually understands Python even more than it does C. So I can actually fix this with that additional in keyword, which I forgot. And now I can see the exact same kind of tabular output, which again prints out capital A as 65. So not necessarily a useful program other than to show us this equivalence. Well, what about arguments at the command line? Let me go ahead and implement a program similar in spirit to argv0.c a while back, this time calling it .py. And in here, let me go ahead and do this. And actually, let me go ahead and import sys first. So sys is a system module that has a lot of lower level functionality, among them command line arguments, which again, we do not declare as being part of main. They're globally accessible, if you will. I'm going to go ahead and do this. If the number of command line arguments in that list there equals 2, then I'm going to go ahead and print out hello placeholder, and then format inside of that sys.argv bracket 1. So if there are 2 command line arguments, something, something, I'm going to print the second of those because the first of them is going to be the program's name or the file's name. Else, I'm going to go ahead and just print out generically hello world. Let me go ahead and save that. Run python argv0.py, enter, and voila. We have hello world. Now, as an aside, and just so that you've seen it, there are other ways of outputting strings, because frankly, this very quickly gets tedious if all you're trying to do is plug in some value. Generally, for consistency, I'll still do it this way. But we could have done something like this. And those of you who took, for instance, AP Computer Science A in high school, or a Java class more generally, might know that the plus operator is sometimes used as the concatenation operator to take one string and another and jam them together. And indeed, we could do this as follows. I could now do python of argv0.py and get the same result. But you'll find generally that using the format approach, as I originally did, tends to be a little more sustainable once your code gets more complex. All right, let's do something else. Let's go ahead and print out a whole bunch of command line arguments, just as we did a few weeks ago, this time in argv1.py, which again corresponds to our earlier code. In here, I'm going to go ahead and import the sys module again and do for I in range. And now this time, I'm going to do the length of sys.argv, which, to be clear, is going to give me the number of arguments in the argument vector, in that list called argv, which sounds awfully equivalent to what? Special variable that we kept using in C? You recall, not just argv, but argc. The latter doesn't exist in Python, but we can query for it by just asking Python, what is the length of the argument vector? That means, what is argc? So I'm going to go ahead now and just print out sys.argv bracket I. And if you think through these lines of code, it would seem that this is going to iterate from 0 on up to the number of arguments in that argv vector or list, and then print out each of them in turn. So let me go ahead and run python of argv1.py, enter. And indeed, it just printed out one thing, the name of the program itself. What if I did foo, bar, baz, some arbitrary words, and hit enter? Now it's going to print all of those as well. So this is just printing out, as we did a few weeks ago, all of the words in argv. But we can do something a little neater now as follows. Suppose that in argv2.py, just like a few weeks ago in argv2.c, I wanted to print out all of the characters and all of the words of the command line arguments. I'm going to go ahead and import sys again. And now I'm going to do for s in sys.argv. So here's a new approach altogether. And then do for c in s. And then in here, I'm going to do print c. And then eventually, just print a new line. So now things are getting a little magical, or frankly, just a little convenient. I'm still importing the sys module so that I have access to argv in the first place. And it turns out that insofar as sys.argv is just a list, like in C, it's similar in spirit to an array, I don't have to do the for loop with the int I and then index into the array using bracket I. I can get from Python's for keyword this beautiful feature whereby if I just say, much like the ranges I've been using it with thus far, for s in sys.argv, this is going to assign s to the first string in argv. Then on the next iteration to the next string in argv. Then on the next iteration, the next string in argv, each time updating s. Meanwhile, on line 4 here, which is indented as part of being inside this outermost loop, for c in s, well, it turns out that Python treats strings similar in spirit to C as sequences of characters. But rather than put the burden on you to declare an int called I or j or whatever, and then iterate over bracket I or bracket j in each of these variables, you can just tell Python, for each character in the string for C, and this could have been any variable name altogether, in the current argument from argv, go ahead and just print out C. So again, here we see another hint of the ease with which you can write code in a language like Python without having to worry nearly as much about low-level implementation details about random access and square bracket notation and indexing into these arrays effectively. You can just allow the language to hand you more of the data that you care about. So let's run Python of argv2.py enter. And it looks a little weird, but if I increase the screen, you'll see that it printed one character per line, exactly those command line arguments. And if I do foo, you'll see argv2.py space foo. It's doing the exact same thing. So not a useful program, but it indeed is allowing us to actually access those characters and strings still. So let's just open up an example I wrote in advance to demonstrate one other point altogether. If I go into week 2's folder here from this week and go into exit.py, you'll see this example. It doesn't do all that much, this program, but it does seem to check this. On line 4, it checks the length of sys.argv, and if it doesn't equal 2, it yells at the user. Missing command line argument, and then it just exits. So just like in C, we have the ability to return an exit code to the shell, to your prompt, not using return as we did in C. You still use return in Python, but to return from methods or functions. In Python, when you want to exit the program altogether, because there is not necessarily a main function, you just call exit and then pass inside of its parentheses the number that you want to return. The convention, as always, being 0 for success and anything non-zero for failure. And so that's why I'm arbitrarily, but conventionally, returning 1 here to the prompt. I'm exiting with an status code or exit code of 1 to indicate as much here. Otherwise, I'm just printing out whatever the word is. So if I run this program and I go into today's second directory and I run Python of exit.py, missing command line argument, and you might recall this trick from a few weeks back. If you, at your prompt, run echo $?, it will show you the exit code of the most recently run program. So if I run this correctly this time with, for instance, my name, and it says hello David, and now I do echo $?, I should see a 0. So just a lower level way of seeing what's going on underneath the hood. Well, let's go ahead and do another example demonstrating what also has changed for the better. Let me go ahead and now do this. In a file called compare1.py, which will line up, you'll find, with compare1.c a few weeks back, I'm going to go ahead and import the CS50 library. I'm going to go ahead and print out just quote unquote s, and then kill the new line, and then use s get cs50.getString. And then let me do this once more with a t variable, also getting rid of the new line just for aesthetics. And then t gets cs50.getString. And then let me go ahead and do a sanity check. It turns out, and you would only know this from reading our source code or the documentation therefore, it turns out that getString could return a special value. It's not null, because Python does not have pointers. We don't have to worry about addresses anymore per se, but it does have special sentinel values like this one. If s does not equal none, with a capital N, and t does not equal none. Indeed, none is a special value similar in spirit to null or similar in spirit to false, but different from both. It's not a pointer, as it is in C, and it's not a Boolean. It's sort of the absence of a value. And indeed, we, in designing the CS50 library for Python, decided that if something goes wrong with getString, maybe the computer or the interpreter is indeed out of memory, even though there is no notion of allocating memory per se, but something goes wrong inside of getString for whatever reason, these calls could return none. So I'm just, for good measure, checking that s is not none and t is not none, so that I can indeed trust that they're indeed strings, so that I can now do something like this. If s equals t, then print same, else print different. And you will recall, perhaps, that when we did this in C some time ago, this did not work. In the world of C, line 10 would not have worked as intended, because it would have been comparing to pointers, to memory addresses. And insofar as in C, getString returns two distinct addresses, even if the user types the same word as we did a few weeks back, it's going to use the heap via malloc to give you two separate strings somewhere in memory whose first byte's address is going to be different. And so S and T in the world of C were not the same. But that was never really all that useful. I didn't really care about those memory addresses. I wanted to compare the strings, and I had to resort back in the day to str compare. Well, as we've already seen, you don't need to worry as much about that in Python. If you want to compare S and T, just do it using equals equals, as always, so that when I run this program now and type in Python compare 1.py, something like Zamila, those are indeed the same. But if I instead type Zamila and then my own name, those are indeed different. And so this is as expected, whereby if I type two strings that happen to be the same, and they're both retrieved via two different calls to getString, they're nonetheless going to be compared as expected for equality. Let's do one other thing to demonstrate one other point of Python. Let me go ahead and open up a new file. I'm going to call this copy1.py. And you'll see that it lines up in spirit with copy1.c from a few weeks back. Let me import the CS50 module. Let me go ahead and print out s with new line ending. Let me go ahead and do cs50.getString as before. And let me go ahead and do a sanity check. If s equals none, then let's just exit, because this program is not going to be useful if something bad happened underneath the hood. And now let me go ahead and capitalize this thing, as I tried weeks ago. Let me go ahead and do t gets s dot capitalize, and then print out s, and then a placeholder that I can format with s itself. Then let me go ahead and print out t colon and a placeholder, and then format t itself. And then let me go ahead, just for good measure, and exit with 0, even though that will be assumed to be the default. So what's going to happen here? Let me run this program, Python copy1.py, type in something like Zamila in all lowercase, enter. And you'll see that it's now uppercased just T and not S. Let me go ahead and do another example with like Andy's name. And we've indeed capitalized Andy's name. So what's going on, and what's with all these dots? The only time we ever really got into dots in C was when we had structures or pointers there too. But it turns out that Python is an object-oriented programming language in the sense that it has support for objects, full-fledged objects, really built into it. C just has structs. And structs, by definition, contain typically only data. They will contain fields like dorm or house or name or whatever it is we're implementing, like a student structure in C. But it turns out that in Python and in other object-oriented language, you can have inside of structures, objects as they're more properly called, not only pieces of data, as we'll eventually see, but also built-in functionality. So the syntax, to be fair, has been very weird when we look at strings. But if you trust me when I say a string or an str variable is an object, that object has inside of it somewhere underneath the hood a sequence of characters, whatever I've typed, but it also has apparently built-in functionality. Among that functionality is a function, aka a method, called format. Similarly, do string objects in Python have a built-in function called capitalize that do exactly as you would expect. So in C, we had toUpper, but that operated on just a single character, and the burden was entirely on me to figure out what character in a string I wanted to make uppercase. In Python, this built-in capitalize function for the string class will do exactly what we intend, uppercasing the first letter in a string and leaving everything else untouched. But it turns out that in Python, a string is immutable, which is to say that once it's created, you can't change it. And this is not the case in C. In C, when we used getString or scanf or malloc or created strings on the stack by allocating them effectively as arrays, if we allocated memory on the heap or the stack and put strings there, we could change those strings thereafter. And in fact, the earliest version of this program in C was buggy insofar as it accidentally capitalized both S and T, even though we only intended to capitalize T. But it works right out of the box with Python, at least as implemented here, because it turns out once S exists as a string, that's it. That's the sequence of characters you're going to get. You can't go in and change just one of them. And so what's really happening here when I call s.capitalize is this function is designed underneath the hood by the authors of Python to give you a copy of S, but quickly change the first letter to a capital letter and then return the resulting copy. All of that happens for me. I do not need to use malloc. I do not need to do stir copy. I don't need to iterate over the characters. All of this we get for free, so to speak, with the language. All right. Let's look now at just where else we can go. One of the biggest problems we ran into, recall in C, was near the end of our focus on it. And we started tripping over issues like memory. You'll recall in C, we had this example here, noswap.py. And this program was pretty arbitrary. It allocated an x and a y int and assigned them the values 1 and 2 respectively. It claimed to swap them by calling the swap function. But then even though it said it swapped them, it swapped only copies of those variables. And indeed, the swap function, if we scroll down below the break here, you'll see that it declares two parameters, a and b, that by nature of how C argument passing happens, become copies of x and y, such that a and b do get successfully swapped, but there's no permanent effect on the caller's variables in main's stack frame, because that was fundamentally flawed. And so we fundamentally fixed that with this version here. In swap.c some weeks ago, we instead started passing in x and y by reference, by their addresses, using the ampersand operator to get their address in memory, passing in effectively pointers, as declared here with the star operator. And then we had to use the star operator inside here of swap to dereference those pointers, those addresses, and to go to them and actually change or get the values at those addresses. So this worked. But let me go ahead now and implement in Python something very similar. I've already written this one up in advance in noswap.py, and it looks like the following. I define main up top. I'm not going to bother using the CS50 library because everything's hard-coded here. X and y shall be 1 and 2 respectively. Don't need to mention int again because it's loosely typed, this language. Now I'm going to go ahead and print x is this, y is this, swapping ... passing in x and y. And then I do what's here, swapped. OK, I claim it's swapped. I print them out again. Swap seems to be implemented. I'm a little nervous about this. This seems to really be just an implementation of literally noswap.c. So let's try it to confirm as much. Let me go ahead now and go into this 4th week's directory in Python noswap.py, enter. Indeed, it doesn't seem to work. So it would seem that Python 2 passes these things in by reference. So how do I fix this? Unfortunately, the fix isn't as, and this is kind of an understatement, easy as it was in C to just change these arguments to be by reference and then use pointers to actually dereference them and actually do the actual swap, because we don't have pointers in Python. So in some way, here's another trade-off that's been thematic. We were getting all these new features. Things are relatively simpler syntactically, even though it'll take some getting used to by all means and some practice. But now we've given up that ability to sort of look underneath the hood and change what's going on underneath the hood. So pointers were scary and pointers were hard, and managing memory is risky because you risk seg faults and you might have memory leaks and all of the headaches you might have had with psets 4 or 5 or any number of the challenges we had involving addresses. You really start to bang your head against the wall potentially because you have access to that level of detail. Unfortunately, as soon as it's taken away, we would seem to lose the ability to solve certain problems. And indeed, in this case, can't really solve it in the same way. There are multiple ways we could address this, but let me propose one that has the advantage of introducing a tiny piece of syntax that's pretty cool to see it the first time. So in swap.py, let me go ahead and declare x as 1 and y is 2. Let me go ahead and print out x is this placeholder and then plug in x there. And then go ahead and print out y is this placeholder and then plug in this placeholder there. And now let me go ahead and just say print swapping ... And then we'll come back to this to do. And now I'm going to go ahead and say print swapped boldly. And then print x is this placeholder. X, and then print y is this placeholder, and then format y. So all that remains to do is the interesting part. So it turns out we could do something like this. We could say temp gets x, and then x gets y, and y gets temp, and that would work. it's a little inelegant because now, the beauty of having a swap function before in C was that we were factoring out that logic. We could use it in multiple places, made the code a little more readable. And now in the middle of this beautiful print statements, I've got this mess here. But it turns out that's the right spirit, at least to keeping the solution simple. But notice what you can do in Python. It turns out that you can actually swap two things at once. And it's because of a feature that's implicit in this syntax here, that these are actually data types on each side of the equal sign. It turns out that Python supports not just lists, which we've generally known thus far as arrays in C, but it also supports, again, tuples, a data structure that allows you a comma-separated list of values, the burden of which is entirely on you to remember what comes first, what comes last, what's in the middle. But by way of doing this, and I can do this in a couple of different ways, and I can do it not even just with tuples, you can think of this a little more like this, like an xy coordinates, Cartesian plane, and so forth. You can actually consider this as happening really simultaneously, but letting the language, Python, and its interpreter figure out how to do that switcheroo without losing one or both of the variables in the process. It doesn't matter to us, the low-level implementation detail, that might actually require some kind of temporary storage. That is now a feature of the language that we get for free if we actually want to assign two values simultaneously. And this is actually powerful for that same reason. It turns out that if you have some function called foo that returns a single value, you could do something like this to get back that value, as we've been doing all throughout these examples. But it turns out foo could potentially return two values, which you could assign like this. Or foo could return three values like this, if foo is indeed implemented as returning a tuple, a comma-separated list of values like this. So you don't want to take this necessarily to an extreme, but in C, you might recall that we did not have this capability of being able to return multiple values, and that is now an option, although there's alternatives to needing to do that altogether. So we're almost caught up in time in Python vis-a-vis where we started and where we ended with C. But let's introduce one other feature of Python that allows us to translate something from C as well. Recall that we introduced structures some time ago. And indeed, I'm going to go ahead here and save a file called structs 0.py, which is a bit misleading because these aren't technically structures. They're objects, as I'm about to use. But we'll clarify that in a moment. And let me go ahead here and import CS50. And let me also import, using slightly different syntax, this. In a moment, I'm going to create, on the fly, my own Python module, my own class, if you will, called student, inside of which is going to be a class called student, capital S. And first, let's assume that it exists so that I can just take on faith that it will soon exist. And let me give myself a list of students like this, an empty array, if you will, as implied by the square bracket notation here. So new syntax, but what's nice is it's pretty readable. On the left is the variable's name, assigning what's on the right-hand side. We've seen square brackets for arrays or lists more generally. So this just means give me an empty list and assign it to students. Unlike strings, a list in Python is mutable, changeable. So this does not mean that students is forever going to be an empty list. We can add and append things to it, much like a stack or a queue or a linked list more generally. So now let me go ahead and do this. For I in range 3, I'm just going to arbitrarily do this 3 times, just like we did a few weeks ago. I'm going to, in here now, print out print name with no line ending, just to keep things pretty. Let me go ahead then and use CS50.getString to actually get a student's name. Then let me say, hey, give me your dorm with no line ending, just to keep it clean. And then use dorm CS50.getString. And then down here, let me do students.append student name dorm. So this is new now. And we'll come back to this in just a moment. Then after this loop, let's just for good measure do this. For student in students, print the following placeholder is in placeholder, then format student.name, student.dorm. So now things are getting a little more interesting. I have now done a few things in this program. I have imported something called a student, which doesn't yet exist, but will in a moment. I've declared a variable, or a list specifically, called students, and assigned it an empty list. Then I'm iterating 3 times arbitrarily, just so we have a demo to play with, saying, give me your name, give me your dorm, and then this. So students is an object, as we say, a structure in C, but now we call them objects. inside of which is going to be data. There's not much data now. It's just an empty list. But it turns out, if you read the documentation for Python, you'll see that a list has some built-in functions or methods as well. Not just data, but also functionality, one of which is called append. And if we read the documentation, we see we can pass in an argument to append that is a variable or a value that we want to append to the list, add to the end of it. And we'll see in a moment what this syntax means. It turns out this is similar in spirit to using malloc in C to malloc a struct and then put inside of it two values, name and dorm. But what's nice about Python and languages like PHP and Ruby and Java, all of which support something similar in spirit, is this single line gives me a new student object inside of which is that student's name and dorm as strings. Later, outside of this loop, just for good measure, we reiterate over this list as follows. For student in students, well, what is this doing? This, again, is an iteratable list. So not iteratable list, whereby you can iterate over this list, calling each element inside of it temporarily student, as in our previous use of for, and then just print so-and-so is in this dorm, formatting those two values using the same dot notation as we used in C. So we need a student object. Otherwise, what's going to happen? Let me go ahead and try to run this incorrectly as follows. Python struct0.py, enter. Import error, no module named student. So creating a Python module, turns out, is super simple. I create a file called student.py. I now have a module called student. Of course, there's nothing in there, so I need to actually populate it. So let me go ahead and do this. And we'll come back to this in the future with a bit more complexity. But for now, let me introduce, with a bit of a wave of the hand, the following. If I want to create a structure called student, technically in Python, it's called a class. And that class shall be student, the convention of which is to call your structures in Python, or your classes, with a capital letter for the first letter. And now I'm going to define a standard method called init that takes as its first argument a parameter that's conventionally called self, and then any number of other arguments that I want to pass it. And then inside here, I'm going to do self.name gets name, and self.dorm gets dorm. So this is perhaps the most new looking piece of code that we've seen thus far in Python. And we'll explain it just at a high level for now. But in line 1, we're saying, hey, Python, give me a new structure. Give me a class called student, capital S. Line 2, hey, Python, inside of this class, there shall be a method, a function, that's called init for initialization. And it's going to take, by convention, 3 arguments, the first of which you just have to do, let's say for now. The second and third and beyond of which are completely up to you. Name and dorm is what I chose. And what's neat is this. Lines 3 and 4 mean whatever the user passes into me as a student's name and dorm, when this class is instantiated, allocated as an object, go ahead and remember their name and dorm inside of these instance variables called self.name and self.dorm. So if you think of the scenario as follows, in struct0.py, we had this line of code toward the end. Not only were we appending something to the list called students, we had this highlighted portion of code. Capital student, open paren name, comma, dorm, close paren. That is similar in spirit, again, to calling malloc in C, and automatically, all in one breath, installing inside of it 2 values, name and dorm. So if this is similar in spirit to malloc, you can think of this line here, this highlighted portion, as creating somewhere in memory in your computer, doesn't matter where, a structure like my fist here, passing into it name and dorm. And then what happens on those 2 lines of code in student.py, lines 3 and 4, is if name and dorm are the 2 values that were passed in, they get stored inside of this structure and saved permanently in what are called instance variables inside of self. Self just refers to the object that has been allocated. So we'll come back to that before long, but just take on faith for now that init has to be the name of the method that you use. Self is the conventionally used as the first argument there. And this just ensures that we're remembering a student's name and his or her dorm as well. So if I now run this, you'll see I'm prompted for David. And I'll say Mather. and Zamila in Courier, and Rob in Kirkland, enter. And the program doesn't do all that much, but it manipulates and it creates these objects and ultimately does something useful with them. But it throws the information away. And so for our command line examples here, let's do one final example that improves upon that as follows. Let me go ahead and create a new file called structs1.py, similar in spirit to what we did some time ago in structs1.c. I'm going to start with that same code from before, and I'm going to keep around student.py. But instead of just printing it, you know what? I'm going to get rid of the printing of these names. I'm going to instead do this. File gets open students.csv, comma w, quote unquote. Writer gets csv.writer file for student in students, just as before. Writer.writeRow student.name student.dorm file dot close. OK, definitely a mouthful. And it's not perfect yet. But let's try to glean what I'm doing. Open turns out is similar in spirit to fopen from C. And it takes two arguments, just like in C, which is wonderful. The name of the file to open and the mode in which you want to open it. Writing, W, or reading, R. And there's a few other options, too. This just returns to me a reference to that file somehow. And indeed, all this time, I've been describing variables as just that, variables. But technically speaking, all of these variables, x and y, and now file, and s and t, and others, are references or symbols that have been bound to objects in memory, which is just to say that you'll see online, especially when reading up on Python, that there's certain terminology that's associated with the language. But at the end of the day, the ideas are no different fundamentally from what we've been doing in Scratch and in C. These are just a variable called file. Here's another variable called writer, and it is storing the return value of csv.writer file. So what's this? I only knew this by reading up on the documentation because I was curious in Python. How do I actually save my data inside of a CSV, comma separated values file? This is sort of a very super simple Excel file that just uses commas to separate what are effectively different columns in a file. So my goal here is to ultimately print David, comma Mather, enter. Zamila, comma Courier, enter. Rob, comma Kirkland, enter. And that's it. And save it permanently on disk, if you will, so that we actually keep this information around. So what does this do for me? It turns out that Python comes with a built-in feature called the CSV module, inside of which is a whole bunch of functionality, some of which is this one here, a class called writer that takes one argument when you instantiate it called file. So this just means, hey, Python, give me a writer for CSVs. Give me an object whose purpose in life is to write CSV files to hard drives. Iterate over my students for student in students. And then just from reading the documentation, I know that I can call writer.writeRow, which is a bit hard to say quickly several times, but writeRow. And then it takes as an argument a tuple in this case. That's why there's the double parentheses, a tuple, a comma separated list of values, in which in this case I want to be student.name and student.dorm. Then I close the file at the end. So the net result here is kind of underwhelming to run. And indeed, we're about to see a bug. Python structs1.py enter. David, Mather, Zamila, Courier, Rob, Kirkland. Damn it. After all that input, then there's an error. But this is actually illustrative of another feature or design aspect of Python. I'm not necessarily going to get compilation errors. I might actually get runtime logical errors. If I have made a mistake in my program that isn't something super simple or dumb or frustrating, like leaving alpha parenthesis or misplaced comma or something like that that's syntactically invalid, Python might not notice that my program is buggy. Because if it scans my code top to bottom, left to right, and doesn't notice some glaring syntax issue, it might proceed to just run the program for me. That is, interpret the program. Only once the Python interpreter gets to a line of code that syntactically is correct but confuses it, might it bail out with a so-called runtime error, or more properly, throw an exception, this one saying name CSV is not defined. And indeed, if I scroll up, the first time I mentioned CSV was indeed on this line with the x, undefined variable CSV. You know what? I messed up. I should have imported the CSV module. And I would only know that from the documentation, but I can infer as much from the fact that CSV does not exist. Let's try this one more time. David, Mather, Zamila, Courier, Rob, Kirkland, and enter. Nothing seems to happen, but notice students.csv has now appeared. And indeed, I have David, Mather, Zamila, Courier, Rob, Kirkland. I have my own tiny little database. It's not a database in a particularly fancy sense. I can't query it. I can't change it very easily. I have to just rewrite the whole thing out, essentially. But I have now persisted this data. And never before in these Python examples have we kept any of the information around until now, much like the equivalent C version. So guess what else we can do with Python? Not only can we re-implement all of weeks 1 through 5's examples from C in Python, so can we implement the entirety of our recent spell checker. For instance, you may recall that the staff solution for speller was run a little something as follows at the prompt, whereby we specify optionally a dictionary, but I'm going to go ahead and use the default. And then I can spell check something like austinpowers.txt, which in the CS50 staff solution, which this one happens to use a try, took me a total of 0.05 seconds to spell check a pretty big dictionary with 19,190 words. But it took me a long time to implement that try. And it probably took you quite a while to implement your try, your hash table, or linked list, or other data structure. But let me propose that today we have in our speller directory a re-implementation of speller in Python. And this was the program you didn't need to worry too much about in C. Speller.c we asked you to read through and understand, but you didn't need to change it. And so indeed today we won't change it either. But I'm going to go ahead and create a file called dictionary.py, inside of which is going to be my very own implementation of this dictionary. And it turns out in Python, we can implement speller as follows. Class dictionary, thereby giving me really the equivalent of a structure, much like we have in C. And I'm going to go ahead inside of this and declare a function that's by default and convention called init. That takes in one argument, in this case called self. And I'm going to simply do self.words gets sets, where set, it turns out, is a function in Python that returns to me an empty set, a collection of values that facilitate, generally on the average case, constant time lookups of whether something's there and constant time insertions of putting something into that set, much like a mathematical set. I'm now going to go ahead and implement my load function in Python as follows, whereby I take in self as an argument, as before by convention, but then also the name of the file to use as my dictionary. And similar to C, I'm going to use a function like fopen, but this time called open, where I simply pass in dictionary and quote unquote r. And then for each line in that file, I am going to access the set called words and add to it the line I've just encountered after stripping off the trailing new line. Then I'm going to close the file, and I'm going to return true, and I'm going to have finished my homework for load. With just those few lines of code, can we re-implement the entirety of the load function for problem set 5 speller dictionary in the load in Python itself? Now, the check function, maybe that's where the price is paid, right? Maybe the trade-off is check's going to be really, really scary. So I'm going to implement this one as a method inside here too, taking in a word that we want to spell check. And I'm going to return word.lower in self.words. And that's it for the check method. What is this doing? This is saying return whether true or false, whether the lowercase version of the given word is in my own word set. So self.words just refers to this container that's initially empty, but that has just been populated by the load method by adding in all of the words that we loaded from that file. So this, true or false, is implemented as follows. Lowercase the given word, and check whether it's in that set. And return true or false in just one line. Well, all right, maybe size is going to be where the price is paid. Maybe size is what's really broken here. So let's go ahead and implement size. And let me return self.words. All right, that one's perhaps not a surprise, since size in C is also pretty easy. But what about unload? Well, how about in unload, we similarly declare it. Well, there's nothing to unload because Python does all of your memory management for you. So even though you might be allocating more and more memory as you use this set, there's nothing to actually unload because the interpreter will do that for you. So it turns out that all of these conversions from C to Python are useful in part because clearly you can implement the same kinds of programs that we've been implementing for a week, and frankly, in many cases, more easily and quicker, or with fewer lines of code, or in a way that's just much less painful to write. Like all of that low-level stuff where you're implementing hash tables or trees or tries is wonderfully illustrative of how those things work and hopefully gives you a true understanding of what's going on underneath the hood. But my God, if you just wanted to store words in a dictionary, if you had to implement dozens of lines of code to implement your own trie or your own hash table or linked list, programming very quickly devolves into an incredibly mundane, frustrating profession. But in this case, do we begin to see hints of other languages, Python among them, that allow us to solve the same problems much more quickly, much more efficiently, much more effectively, much more pleasurably, such that now we can start to stand on the shoulders of even more people who've come before us, start building on not only this language, but on other APIs and libraries. And indeed, that's now why we introduce Python. No longer in the weeks to come are we going to be focusing on the command line alone, but rather on web-based interfaces. Indeed, in Python do we have the ability to so much more easily than in C write web-based software, actual websites that are dynamic, not just built out of HTML and CSS, but that have shopping carts and use databases and send emails or SMSs or any number of dynamic features, all of which, to be fair, we could implement in C. But it would be the most painful experience in the world to implement a dynamic website with all of those features in a lower level language like C. But with Python, can we start to do this so much more readily? So how do we go about using Python to generate websites? A couple of weeks ago, when we first looked at HTML and CSS and talked more generally about HTTP, we hard-coded everything we wrote. We wrote HTML in our text editor. We wrote CSS in our text editor. We saved those files, and then we loaded them using our browser, but there was nothing dynamic about it. There was no even hello world program that dynamically took my name. But we did discuss in the context of HTTP this ability of web browsers and web servers to use HTTP parameters in order to transmit inputs in between the two. For instance, we talked about get, whereby you can pass in these key value pairs via the get string, the query string in the URL itself. We talked a bit about post, whereby you could transmit more sensitive information or bigger things like photographs and passwords and confidential information via post, which is still passing in key value pairs from browser to server. But we didn't at the time have any ability to actually read or parse those inputs and produce dynamic outputs. In fact, the most dynamic we got a couple of weeks ago was with those search examples whereby I re-implemented the front-end interface of Google, sort of our very low-budget version of Google's web site, and then I just completely punted to their backend using the action attribute of https www.google.com/search, pretty much deferring entirely to Google all of the interesting dynamic output for my search results. So today, we won't generate those search results ourselves, but we will give ourselves, now that we have a language and the environment with which to handle those inputs, we will give ourselves the capability to start creating websites more like that. In fact, ultimately, the goal of creating a web-based software is to dynamically output stuff like this. This, of course, is the simplest program we could, or the simplest web page we could perhaps implement in HTML, but it's entirely hard-coded. Wouldn't it be nice if we could minimally, for instance, add someone's name dynamically to that output so that it actually interacts with them in some way? And you could, of course, extrapolate from that kind of feature to things like Gmail, where it's constantly dynamically interacting with your keyboard input based on who you put in the to field, what you put in the subject line. The website's going to do and behave differently in order to send that mail. Facebook Messenger or GChat or any number of tools are constantly taking web-based input from users and producing dynamically output. But how do we get at that input and output? Especially since at the end of the day, this is all HTTP boils down to. Inside of those virtual envelopes, so to speak, going between client and server or browser and server are requests like these from the clients. Get me the home page using this version of HTTP, specifically from this host name here, and then maybe some other additional detail and maybe some parameters in that URL string. Meanwhile, the server is going to respond similarly with something pretty simple, a textual response, some HTTP headers like this, saying the content type is text HTML, if it indeed is, followed by the HTML that the server has generated. So it would seem that we need the ability, when writing web-based software, to be able to, one, dynamically generate HTML based on who the user is or what he or she wants to see dynamically. So we have the ability to write HTML, of course, per 2 weeks ago, but we haven't yet printed it or generated it dynamically. And we're also going to need a feature whereby somehow or other any HTTP parameters coming to us from browsers can be interpreted so that if a user is trying to add something to their shopping cart, we can actually see what it is they've requested to add to their shopping cart. So it turns out we need just one mental model, if you will, for this world of the web. Back in the day, this mental model didn't necessarily exist, but over time, we humans have come up with certain paradigms or design patterns, so to speak, that guide common implementations of web-based software or mobile software, because the world realized over time that they adopted certain habits, or there's certain convenient ways to implement software. And one such method, or one such design pattern, is generally called MVC, Model View Controller. And in this world, the controller is really where the brains of your program or your website are. All of the logic, the logging in of users, logging out of users, adding things to a shopping cart, removing things, checking out, billing them, all of that is sort of business logic, so to speak. And that exists in one or more files, typically, on a web server that collectively are called the controller. So it's not a technical term per se. It's just a descriptor for what your code is ultimately doing. View, meanwhile, the V in MVC, refers to the aesthetics of your site, typically, the templates that you use for HTML or the CSS files that you use in order to style your website. In other words, while the thinking, all of the code logic might be embedded in files called your controller, all of the sort of fluffier but still important stuff, the aesthetic stuff, might be in the view side of things. And then lastly is the M in MVC model, which is where your data typically comes from. So we just did an example using a CSV file. That's a model of some sort. It's a super simple model, but a model is just a general term describing where your data lives and how you access it. And before long, we're going to use a fancier version of a model, an actual database server that we can query and insert into and delete from and edit in any number of other features as well. But for now, today, let's just focus on the C and the V in MVC as follows. I'm going to go ahead and open up CS50 IDE, where we have a simple program here called serve.py. And this is perhaps among the lowest level ways we could go about implementing our own web server. So again, CS50 IDE comes with its own web server, and Google has its own web server, and Facebook has its own web server. And many of them are using, like us, open source software, freely available software that's super popular. But suppose we want to implement our own web server that listens on TCP port 80 for HTTP requests for those virtual envelopes. In Python, we might do it as follows. And a lot of the words on the screen might be new, but the syntax is fundamentally the same as what we've been focusing on today. So from some module that comes with Python called HTTP server, import a class called base HTTP request handler and HTTP server. So it turns out that Python comes with some built-in web server functionality. It's not all that user-friendly, as we'll see. We have to do a lot of work to use it, and the names are fairly verbose unto themselves. But it comes with the ability as a language to let you implement a web server, a piece of software that when you run it just starts listening on the internet on your computer's IP address on TCP port 80 for incoming HTTP requests, and then responds to them as you see fit. So we've defined a class here called HTTP server request handler that descends from this parent class, so to speak, but more on that in the days to come. On line 7 here, I'm defining a method conventionally called doGet, where get is capitalized, thereby making super clear that this is the function, the method, that's going to be called if our server receives a request via HTTP GET, as opposed to POST or something else. Self is, again, the convention when implementing a class for methods to take in a reference to themselves, so to speak, a reference to the containing object, we'll just call self. Now, inside here, and you'd only know this from having read the documentation or having done this before, notice that we're going to do a few things in this web server. Super simple. We are going to, no matter what, just send a response code, a status code of 200. Everything is always OK in the server. It's not realistic. Things could certainly go wrong, especially if the user asks us for something that we don't have. A 404 might be more appropriate. But we're going to keep the example simple, and no matter what, send 200 OK. Meanwhile, we're also going to send another HTTP header using this Python call here of self.sendHeader. And to be clear, these features, send response, send headers, soon end headers, are methods or functions that come with Python's built-in web server that we are simply extending the capabilities of at the moment. What is the header that we want to send? Content type, text HTML. So we're going to behave exactly like that canonical example I put up again a moment ago. Lastly, we're going to send a super simple message. We are simply going to write essentially to the socket connection that my server has with the browser, the internet connection that we have. I'm going to write the following bytes. Hello, comma, world. And I'm going to use an encoding called UTF-8, which is a way of encoding Unicode, which again is an encoding scheme that's a superset of ASCII, as we discussed back in week 0. And that's it. Return. Now, this just defines a class, my own customization of a web server. Python comes with a web server built in, specifically that class called base HTTP request handler. And I'm simply extending its capabilities to specifically return hello world with content type text HTML and with a status code of 200. That wouldn't necessarily be the case by default, certainly not that generic message. But I have to start this server. And I could add a main method and I could add a main function or implement this in any number of ways, but I'm going to keep it simple. At the bottom of the file, I'm going to configure the server here, hard coding port 8080 to be the value of this variable. A server address here is going to be a tuple, and you would only know this again from the documentation. This tuple, this comma-separated list of values is going to be this weird-looking IP address, and then that same value, 8080. And this weird-looking IP address is a convention. If you specify that you want a web server to listen to talk on IP address 0.0.0.0, that's generally shorthand notation for saying listen on all possible network interfaces that are built into my computer, whether it's CS50 IDE or an actual server or a Mac or a PC. This is sort of like the wild card saying just listen on any one of your Ethernet cables or Wi-Fi connections for incoming requests, but specifically on this port 8080. This last line here essentially instantiates an HTTP server, passing into it our request handler, which is that customization of behavior that I described earlier. And then lastly, and nicely enough, there's a method, a function built into this Python server called serve_forever, which just turns the server on and never turns it off, unless I forcibly kill it with, say, Control-C. So let's go ahead and actually run this. I'm going to go ahead into the folder containing serve.py and run python serve.py, enter. And nothing seems to happen just yet. But I'm going to go ahead and open up another tab in CS50 IDE. And I'm going to go to http://127.0.0.0:8080. So why this IP address? Even though this is a little inconsistent with what I just said, technically 0.0.0.0 is not your actual IP address. It's, again, just kind of a wildcard string that represents all of your possible network interfaces. Every computer on the internet generally has a local host address, not its public IP, not even a private IP that's in your own home network behind your own firewall, but 127.0.0.1 represents your own local host address, an IP address that by default every computer on the internet has insofar as it refers to itself. So we all have generally in our own Macs and PCs or CS50 IDEs access to this IP address, which just refers to myself. And port 8080 after the colon. Normally using a browser, you don't specify the port number by saying :80 or :443. But in this case, because it's a non-standard port, what I want to do with Google Chrome here is talk to my computer on this local host address on that port. Now, if you play along at home using CS50 IDE on the web, your address will actually be different. I simply happen to be using a local version of CS50 IDE on my own Mac here so that I don't have to combat with any Wi-Fi issues. But the idea is going to be exactly the same. Whatever your workspace's IP address is or host name, the English version of it, :8080 is what you will type. Let me hit enter. But it's not all that interesting. Indeed, if I view the page source as we have in the past, this is not HTML. I've been super lazy right now, simply outputting a promise via that header that I'm outputting a content type of text HTML. But this isn't really HTML. This is just text. And so this really isn't a full-fledged web server. It's certainly not dynamic in that I've literally hard-coded hello world. So let's do something a little better, a little more pleasurable to write. And for that, we're actually going to need something called a framework. And so it turns out that writing code like this, totally possible, and folks did it for some time, but eventually did people realize, you know what, we're doing the same kinds of lines of code again and again. This isn't particularly fun to implement the website or the product that I'm working on. Let me actually start to borrow ideas from past projects into current projects, and thus were born things called frameworks. Collections of code written by other people that are often free or open source, that you can then use in your own projects to make your life easier. And indeed, this is thematic, especially as we get farther and farther from C and lower level languages toward Python and eventually JavaScript and beyond. You'll find that it's thematic for people to sort of stand again on each other's shoulders and use past problems solved to solve future problems more quickly. So what do I mean by that? Well, one of the very first things I did way back in the day when learning web programming myself, after having taken CS50 and CS51, is I taught myself a language called Perl. It's not really in vogue these days, though still around and still under development, but it's similar in spirit to what we're talking about today in Python. And I happened to use that language back in the day to implement a website, the first ever website for the freshman intramural sports program. So all the freshmen or first years who want to participate in sports just for fun, back in my day, we would register for sports by walking across Harvard Yard, uphill both ways in the snow, and then slide a piece of paper under one of the proctors or RA's doors saying, I want to register for volleyball or soccer or whatever it was. So this was an opportunity ripe for disruption with computers. So I taught myself web programming back in the day and volunteered to make this website for the group so that students like myself could just, well, maybe students not like myself could register for sports online. And so what did I actually do? Well, we won't look at the Perl version. We'll look instead at a Python version using a very popular framework, a freely available code called Flask. So Flask is technically a micro framework in that it doesn't have a huge number of features, but it's got relatively few features that people really seem to like lately that helps you get work done faster. And by that I mean this. This is how I might implement the simplest of websites for the freshman intramural sports program. Now, admittedly, it's lacking in quite a few features, but let's see how it works. And indeed, with some of our future web-based projects in CS50, will we build upon Flask and borrow these same ideas? So you'll notice that from Flask, am I importing a whole bunch of potential features, none of which I want to implement myself, all of which pretty much I would have had to implement myself if I used that base HTTP web server that comes with Python itself. So Flask is built on top of that built-in functionality. How does it work? Once I've imported this module's components and classes, I'm going to go ahead and instantiate, so to speak, an application of type Flask, passing in the name of this file. So this is just a special symbol, underscore underscore name, that we've seen before in the context of main, that just refers to this file. So this says, hey, Python, give me a Flask application based on this file. So now notice on line 5 a slightly new syntax, something we'll call a decorator. And it's a one-liner in this case that simply provides Python with a hint that the following method should be called anytime the user requests a particular route. A route typically is something like /foo or /bar or /search or the like. So a route is like the path that you are requesting on the web server, / generally being the default. So this is saying to Python, anytime the user requests / the default home page, go ahead and call this index method that technically we could have called anything, but this is a good convention, and return what? The rendering of this template. In other words, don't just return a few bytes, hello world, return this whole HTML file. But it's a template in the sense that we can plug in values, as we'll soon see. Meanwhile, hey, Python, when you see a request for /register, not using get by default, but by using post, which might happen in a form submission, go ahead and call this method called register. And just as a sanity check, let's do this. If the request that we have received has a form in it, that has a name input in it that's blank, equals quote unquote, or the request we've received has a form whose dorm field is blank, then return this template instead, failure.html, otherwise return success. So in other words, if the user has submitted a form to register for sports, and he or she has not given us their name or their dorm, let's render this failure message. Don't let them register, because we don't even know who they are, where they're from. So we're going to display failure.html. Otherwise, by default, we'll display success.html. layout.html. So let's see what this looks like. I'm going to go ahead and hit Control-C to get out of the old web server. I'm going to go into this frosh.ims directory. And this time, instead of running Python, I'm instead going to run Flask, run. And then I'm going to be just super specific here. I'm going to say the host I want to use is every possible interface. And then the port I'm going to use is 8080, though you can configure these in different ways. And I'm going to hit Enter. A whole bunch of stuff scrolled on the screen. But the essence of it is that serving Flask application, debug mode in CS50 IDE is turned on by default at the moment. And now we're ready to go. If I now go back to my web page and reload, I'm still at the same URL, but a different web server is now responding to my requests. And this is sort of in the spirit of 1996, 97, whenever I implemented this. This is what the web looked like. And in fact, this might be a little worse. So now, suppose I'm kind of in a rush. I just want to register for sports. I don't think to provide my name or dorm. Let me hit register. And I'm yelled at. You must provide your name and dorm. And notice, where am I? If I look at the URL, I'm at that same IP and port number, which will vary based on where you are in the world and what service you're using, like CS50 IDE. But I'm at /register, that route. All right, let me go back. Let me go ahead and give them my name at least. David, register. And voila, I am being yelled at again because even though I provided my name, I've not provided my dorm still. So this seems to be a fairly lightweight error message. But let me cooperate. Let me provide both David and say Matthews and click register. Aha, you are registered. Well, not really. So why not really? Well, that's because this particular website has no database yet. There's no place to store the data. There's not even a CSV file. There's no email functionality. All it's being used for today is to demonstrate how we can check for the presence of form submissions properly to make sure the user is actually providing those values. So if I actually go back into CS50 IDE, let's go into this frosh.ims directory, inside of which is a templates directory, and take a look at failure, the first thing that we saw. Now, this admittedly looks a bit cryptic. But for a moment, notice that it's extending something called layout.html. And actually, it looks like there's these special syntax here. So it turns out that Flask supports a templating language. It's not HTML. It's not CSS. It's not even Python. It's sort of a mini language unto itself, a templating language that gives you simple instructions and features that allow you to dynamically plug in values to your HTML. So they don't have to hard code everything. And so this is saying, hey, Flask, go and get the template file called layout.html, and then plug in this title and then this body. So block title here, and notice the funky syntax, curly brace with percent sign with curly brace. This is literally saying, hey, Flask, the title of this page shall be failure, and the body of this page, as per this block here, shall be, quote unquote, you must provide your name and dorm. Meanwhile, if we open up success.html, it's similar in spirit, but notice it has a title of success, and it has a body of you are registered. Well, not really. So nothing interesting is happening, but this body and this title would be plugged into this layout, this other template file. So let's now look at layout.html. Ah, this looks more familiar. So layout.html is sort of the parent of these children, success.html and failure.html. And this is because I realized when designing the frosh.ims website for the first time, I don't want to have to copy and paste a whole lot of similar HTML. I don't want to have HTML in every file, head in every file, title in every file, body in every file. There's a lot of redundancy and a lot of structure to these web pages. It would be nice if I can kind of come up with the general layout, the aesthetics for my overarching website, and then on a per page basis, just plug in a custom title, just plug in a custom body. And that's all this funky syntax is doing. It's saying, hey, Flask, put the body of this page here, and hey, Flask, put the title of this page here. So again, this has nothing to do with Python per se, nothing to do with HTML or CSS per se, except that it is a templating language, another language used for really plugging in values in this way. And it's conventionally used in exactly this context with Python, with CSS, and with HTML. It helps us keep things a little cleaner and avoiding a whole lot of copy-paste. The form, meanwhile, that we originally saw is perhaps even more familiar, except for the block up top. It, too, extends layout.html. It has a title of frosh.ims. And then it's pretty much just got an h1 tag, which you might recall from a couple of weeks back. It's got a form tag. It's got some br for line breaks, a select element, and more. And the only thing that's a little interesting here is notice this. Whereas 2 weeks ago, I hard-coded an action value like google.com/search or to my own file, this is a nice abstraction, if you will, whereby I can say in my template, give me the URL for my register route. Now, realistically, it's probably just /register, because that's what we hard-coded into the file. But it would be nice to not have to hard-code things that could change over time. And so this URL for is a way of dynamically asking the templating language, you go figure out what this route is called and plug in the appropriate relative URL here. So that's all frosh.ims does on the front end. What's the back end? Well, for that, we need to look at application.py. Again, this is where we started. When I submit via post that super simple HTML form to /register, that is this route, first this if condition runs. If the request form's name field is blank or its DORM is blank, return failure, else return success. But this isn't especially dynamic. It would be nice if I keep saying dynamic, that things actually are dynamic. So let's look at one final example. So now let's rerun Flask in this store subdirectory, still on the same IP, still on the same port, but now serving a different application on the same. Indeed, when we now reload the browser, we see not the frosh.im site, but a super, super simple e-commerce site, a web storefront that allows us to buy apparently foos and bars and bazes. This is just an HTML form. These are text fields here. These are just labels on the side. And this is a submit button. And the shopping cart ultimately is going to show me how many of these things I've added to my shopping cart already. Indeed, let's try adding 1 foo, 2 bars, and 3 bazes, and click Purchase. I'm redirected automatically to my cart, and I just see a reminder that I've got 1 foo, 1 bar, 1 baz. And let's just confirm that this is indeed the case. Let me go ahead and continue shopping. And let me go ahead and buy 10 more foos, click Purchase, and indeed it's incremented this properly. And indeed, while you can't quite see what I'm doing on my keyboard, I'm hitting reload now, and nothing's changing. Indeed, if I close the window and then reopen it, you'll see that it retains state. In other words, no matter whether I close or open my browser, it seems to be remembering that I've got 11 foos, 2 bars, and 3 bazes in my shopping cart, so to speak. So how did we implement this functionality? Well, first, notice that the store itself is super simple. It's just some HTML and a template that has a whole bunch of input fields textually for foos, for bars, and for bazes, as well as that submit button called purchased. And it, like before, extends layout.html, which this application has its own copy of. The cart, meanwhile, is actually pretty simple. And notice what's nice about this templating language. It lets us do this. This is a file called cart.html that also descends from that layout. And we have this h1 tag here that just says cart. And now notice this template language looks quite like Python here, has for item in cart, and it allows me using this curly bracket notation, 2 of them on the left, 2 of them on the right, to plug in the quantity field of this item object. So it seems that cart is some kind of list, and item are the elements, the objects inside of that list. And this is giving me the quantity field inside of this structure and the name field inside of this structure. And that's why I see 11 foo and 2 bar and 3 baz in my templating language here. I'm just iterating over what apparently is my shopping cart. Now, this invites the question, what is this shopping cart? And for that last detail, we need to look at application.py. So as before, we instantiate a Flask application up here, but we also configure it with a property called secret key per the documentation for Flask. You probably shouldn't use a value of shh, but for now we'll keep things simple. But that key, long story short, is used to ensure with higher probability the security of the sessions or the shopping cart that we're using. This line here again declares a route for / specifying we only want to accept get and post. Turns out there's other HTTP verbs like put and patch and others, but we're going to ignore those for now. And if that route is requested, call this method store. Meanwhile, that method says, hey, if the request method is post, that is, if the user submitted a form not by get but by post, go ahead and iterate over the 3 possible items that we sell in the store, foo, bar, and baz. if the item is not already in the session. And you can think of session as our shopping cart. It's a special object, dictionary that allows us to store keys and values, a hash table of sorts. Then go ahead and add to the session, the shopping cart, that item, foo or bar or baz, and then as an integer, the number of foos or bars or bazes that the user requested via the form. We're calling int here, effectively casting whatever that value is, because it turns out HTTP, all of those messages going back and forth all this time are purely textual. So even though it looks like 10 or 1 or 2 or 3, those are actually strings. So using int here converts that to the integer. So we're actually storing numbers with which we can do simple arithmetic. Otherwise, if a foo or bar or baz was already in the shopping cart, go ahead with Python's plus equal operator, which C also had, and just increment the count from 1 to 10, for instance, as I did a moment ago, and then redirect the user to whatever the URL is for the cart routes. In other words, after I add something to my cart, let's just show me the cart right away rather than showing me the order form instead. Otherwise, if the user requested this page via get, go ahead by default and just return store.html, which is that simple form that lists the text fields and the numbers of foos and bars and bazes that you might want to buy. Meanwhile, the shopping cart is implemented in this application as follows. Here's a route for /cart, in which case a method called cart is called. We then declare inside of this method an empty list called cart. And then as before, we iterate over the available items in our store, foo and bar and baz. And then what do? We simply append to this cart, this list object, the following. We append what's called a dictionary, a hash table, a collection of key value pairs, simply by associating a name with a item capitalized properly and a quantity associated with the actual number of those items in my session. And then we return this time not just the template via its name, cart.html. We furthermore render cart.html, passing into that template a variable called cart, whose value is also cart. In other words, this variable is going to be called cart, and it's going to be equal to whatever this list is. And it's these two lines here in the for loop that are appending a key value, a set of key value pairs, so that we know how many foos we have, how many bars, and how many bazes. And that's why in cart.html do we have access to on line 9 here a cart list over which we can iterate. So there, we're just scratching the surface of what we can do. But we now have a language with which we can express these new kinds of features. We now have a server environment that allows us to actually execute Python code not only at the command line, but also via HTTP and in turn TCP/IP, and in general over the internet itself. So now using this language and soon a database and soon a client-side language called JavaScript and more, can we start to build the very kinds of websites with which you're probably already familiar and using them every day on your laptops and phones. We're just now beginning our foray into web programming. And next week, we'll be add a backend so that we can actually do all this and more.
I never even got to know him. I don't know what happened. Please, I need to be alone.
The people need to know. There'll only be a few questions.
No, please go. I never did get to have dinner with him at his favorite restaurant.